So we're picking up in the middle of this section, and I told you that I was going to tell you about the Quantum Hotel. The Quantum Hotel is an imaginary discount resort for electrons. And this is located in the fantasy world I call Mrs. K's Chemistry Land. It's a happy place for me. I know Disneyland is the happiest place on Earth. You probably wouldn't agree that Chemistry Land is the happiest place on Earth, but I think it's a pretty happy place. So, the Quantum Hotel. This is a crazy analogy. This is a crazy analogy, which is really not scientific at all, but it should help us remember what's going on. So, the problem with electron configurations and thinking about orbitals and quantum mechanics is it's very abstract. It's hard to get your mind around what's going on here. And so the analogy that I came up with was a hotel. We all understand how the rooms and the floors and everything are organized in a hotel, and it's really not that different from the organization of electrons. And so in this hotel, there are different floors, of course. It's a multi-story hotel. The first floor only has one room. It's kind of a weird hotel, but just bear with me. The first floor has one room, and it doesn't have a number on it. It's got the letter S on the door. The second floor of the hotel has two different rooms, the S room and the P room. The third floor has three rooms, S, P, and D. Guess how many rooms are on the fourth floor? 4, and they're labeled S, P, D, and F. If there was a 17th floor, how many rooms would it have? 17. Okay, the number of rooms is equal to the floor number, right? So we're going to talk about 4 different rooms. The S room, which is, each floor has an S room. The S room has 1 bed in it. Starting on the second floor, each floor has a P room. Also, the P room has 3 beds. D rooms have 5 beds. F rooms have 7 beds, and we don't need to talk about anything further than that. That's a strange hotel room, right? 7 beds in 1 room? Why? I don't know. I wasn't consulted when they built this. So there's some rules. There can only be 2 people per bed. No sleeping on the floor allowed. Okay, 2 people per bed, and those people must have opposite spins. What the heck does that mean? Well, there are a couple of different ways that you could interpret spin in the analogy. I don't want to offend people, so I'm going to go with one that has to do with Fort Snelling in St. Paul, Minnesota. How's that for random? Fort Snelling is an old fort in Minnesota where it gets very cold at night. And it's still there, and you can go and you take tours of it. And you can see where the soldiers slept. They slept in bunk beds, and these bunk beds were not even a full twin size. They weren't twin size even. They were just really small. 2 soldiers slept in each bed. So 1 bunk bed, top and bottom, 4 full-grown men sleeping in there. How do you get 2 men in a twin-size bed? I mean, just the shoulders won't fit next to each other, besides the whole creepiness factor of 2 guys, sleeping together that aren't interested in each other. Well, they would sleep head to toe, because your feet don't take up as much room as your shoulders in your chest, right? So they'd sleep head to toe. So that's my analogy for spin. If you've got 2 people sleeping in this bed in the hotel, one sleeps with their head at the head of the bed, and the other sleeps with their head at the foot of the bed. Okay, so opposite spin. Okay, so that's what that means. So just here's a little key to what the things in the analogy correspond to in terms of electrons and energy levels and stuff. Each floor in the hotel is equivalent to a principal shell in the atom. The beds are like orbitals. I'm sorry, I skipped this one. Each room is a subshell. Each bed is an orbital, and the people in the hotel are the electrons. And energy this should be flipped. Money represents energy. So just like in a regular hotel, a normal hotel, not all the rooms cost the same amount of money, right? You get a larger room, a room with more amenities, one on the penthouse, the top floor that's huge, it's going to cost more, right? These different floors and the different rooms, they cost different amounts of money to stay in. So now if we look at this diagram, which may have just looked very random when you saw it on Tuesday, I see this as being a schematic of the hotel. And this is, you know, it's a crazy hotel. It's shaped kind of like an inverted pyramid. You wouldn't want to build this in California because the first little earthquake and things are going to topple over. The bottom floor has one room. There's the S room. 1S because it's on the first floor. The second floor has a 2S room, and this is the 2P room, and it's got 3 beds. So each of these lines is a bed. You can put 2 people in a bed, but they have to have opposite spins. The pricing here is as you go up, the price gets more expensive. As you go up, the energy gets higher. So 1S is the lowest cost, 2S is next lowest, then this one, and then this one, and this one. Now, this 4S room is actually cheaper than staying in the 3D room. Why? Because the hotel manager decided it. It's just that way. And then we've got this one, and this one, and this one. So what happens is this is a discount resort. The electrons that are coming to stay here are looking for the best price. They don't really care. They're going to go off and play in the ocean or skydive or something. They're not going to hang around in the hotel. They don't care about the nicest room. They're trying to stay cheaply. So let's think about perhaps a group of 16 electrons comes to stay in this hotel. And I'm going to represent them as little arrows. So 16 electrons. How are we going to accommodate them at the lowest cost? Well, this 1S room has 1 bed. We can put 2 electrons in there, but they have to sleep head to toe, opposite spins, right? So we got one guy there and another one here. The next 2 electrons are going to go into the next most expensive room. They're going to go for the cheapest one that's still available. So we'll put 2 in there. And now the next electrons are going to go to that 2P room. So as they're coming into the room, here's one electron. He's like, I'm taking that bed. The next guy comes in. Is he automatically going to sleep with this other electron head to toe in this bed when there's 2 empty beds? No. He's going to go take his own bed. So he's going to go over here, and the next guy's going to take his own bed. The next electron that comes in, remember, cheapness, discount is their focus. So the next guy isn't willing to pay extra to go to a more expensive room so he can have his own bed. So he's going to come in, he's like, well, they're all full, I'll just jump in with this guy. And then the next one will go here, and the next one will go here. Does that make a little more sense than the boxes in the orbital diagrams? Can you at least kind of picture what's going on? So how many electrons do we have here? 2, 4, 6, 8, 10. So I said there was a group of 16. So we got 6 more. So the next 2 are going to go in this room. They have to sleep head to toe in the bed, opposite spins. So that's 2, and I've got, 4 more left? So we go up here. The next guy is going to take his own bed. And this guy's going to take his own bed. We've got 1 guy left, and he's going to bunk up with one of them. Probably the one closest to the door, because why not? Any questions? Now, we can take that and write down more concisely, like maybe the desk manager, the guy at the desk, would keep track of who's in the rooms, which rooms are fully occupied, so that when more electrons come in, he's not going to send them to a room that's already full, right? So this is what's going on in the hotel. The manager downstairs is going to keep track of what's going on. So he's going to say, oh, well, the 1s has 2 electrons in it, and the 2s has 2 electrons in it, and the 2p room has 6 electrons in it. What am I writing here? What's that called? Electron configuration. And then the 3s room has 2 electrons in it. How many electrons in the 3p room? There's 4 arrows, right? 1, 2, 3, 4. This is the electron configuration for 16 electrons. Which element has 16 electrons? Sulfur. This is the electron configuration for sulfur. We could draw an orbital diagram, too. In the orbital diagram, each bed is a box. So there's the 1s bed, and there's a 2s bed. In the 2p room, there's 3 beds. So we're just going to draw them all next to each other, because they're really in the same room. Then there's the 3s. There's 1 bed in there. And then the 3p has 3 beds. And so if I was going to place electrons in there, we'd take that, fill up that room first, and then this room, then this one. And so they're filling singly with parallel spins. I believe that's called Hund's rule. And then they're going to pair up when they have to. And then this one's going to be full, and they'll go in here like that, and then this one will be upside down. That's the orbital diagram for sulfur. Yes, question?
And if there's more electrons, would it go to the 4s first?
Yeah, if we continue adding electrons, the next one will go here and here to fill up this 3p. Then they'll go to 4s before they go into 3d. Because this is lower in energy. In the hotel analogy, this room's cheaper than that room. You might say, well, why? It's got 1 bed. You've got more privacy. It doesn't have to make sense. It just is. There are reasons in the atom that this energy level, this subshell 4s, is lower in energy than 3d. It has to do with electron shielding, penetration of orbitals, and all these different interactions, which you probably don't want to hear about. What I will show you in a minute, though, is that this order, how you can remember that 4s is before 3d, we can actually see it in the periodic table. It's just hiding. Any other questions? Do you like the hotel or not? Is it better than just the plain old electron business with the orbitals? What the heck is an orbital, right? This is a different way to remember orbital filling. So if you write this out, 1s, 2s, 2p, 3s, 3p, 3d. So we're just going 1, 2, 3, 4, 5, 6, 7, and then SPD, SPDF. The fourth one has 4 levels. And then the idea here is that you're drawing diagonal lines. Come on. So it's 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, etc. You could do that. You can memorize this. I prefer looking at the periodic table. So I'm going to show this to you right now, and if it works for you, great. Otherwise, forget it. So here's a summary. Lower energy orbitals fill before higher energy orbitals. Electrons in the hotel are going to fill up the cheaper rooms first. If they can get a bed for less, they'll take that. Orbitals can hold no more than 2 electrons. And when the 2 electrons occupy the same orbital, they must have opposing spins. That's the Pauli exclusion principle. In the hotel, each bed can only have up to 2 electrons, and if there are 2 electrons in the bed, 2 people in the bed, they have to sleep head to toe. When orbitals of identical energy are available, all of these are first occupied singly by electrons with parallel spins rather than electrons in pairs, and that's called Hund's rule. So the electron comes in, there's 3 beds, one of them has somebody in it. The electron's going to take his own bed first. The electrons are going to take an empty orbital before they pair up. And they're going to do that with parallel spins. If you're going in and that bed's occupied and I can choose my own bed, the first person is going to get in and they're going to sleep right side up in the bed. The next person who joins them in the bed is the one that has to sleep upside down. My kids like to sleep upside down just for the heck of it, but not in the hotel. Any questions about these guidelines? Okay, so let's practice a little bit. Let's write electron configurations and orbital diagrams for nitrogen, oxygen, fluorine, and neon. I like to do the orbital diagram first, especially at this stage where it's all still kind of new. So let's do nitrogen. How many electrons does nitrogen have? 7. 7 electrons. So I'm going to draw the boxes. So there's 1s and 2s and 2p. So those are the first 2 floors of the hotel. The first floor has 1 room with 1 bed. Second floor has 2 rooms. The first room has 1 bed. The second room has 3 beds. And I'm pretty sure we can fit all the electrons in here, so we don't need to draw any more boxes. So let's put these electrons in here. Let's see. Pick a different color. So I'm going to count to 7. 1. Oh, that's way too fat. See if this is better. 1, 2. He's going to sleep with the first electron because he wants to save money. So that's 1, 2, 3, 4. I'm going to fill up that one. 5. The next electron is going to take his own bed. 6, 7. Those electrons would prefer to be spread out in their own orbitals. So that's 7 electrons. Then writing the electron configuration from the orbital diagram is easier than just coming up with it out of thin air. So how many electrons in 1s?
2.
2. And in 2s?
2.
And in 2p? 3. And then you can check yourself by adding the subscripts. 2 plus 2 plus 3 equals 7. So that means we've got the right number. Any questions about that one? Okay, let's do oxygen. How many electrons does oxygen have?
8.
It's got 8 electrons. So we'll draw boxes again. 1s, 2s, 2p. Now we have to put 8 electrons in. 1, 2, 3, 4, 5, 6, 7. Where's the next one going to go? He's going to go in this first box, and he's going to sleep upside down on the bed. Have to be head to toe so they fit in there. It looks very similar to the electron configuration for nitrogen, doesn't it? Just got 1 more electron. There's an order of filling, and you just follow the same order until you have the right number of electrons. So then, electron configuration, 1s2, 2s2, 2p4. Any questions? Fluorine. 9 electrons. Well, let's try to predict from just looking at electron configuration, where's that next electron going to go? It's going to go in this P. So probably the electron configuration then is going to be 1s2, 2s2, 2p5. Well, I'm getting tired of drawing boxes. This was an orbital diagram for oxygen. I can make it into an orbital diagram for fluorine just by adding one arrow. So if I just add one arrow in here, now it's fluorine, isn't it? It's got 9 electrons. And this diagram, which is now for fluorine, matches up with this. So I'm just going to cross that off so it doesn't look confusing. I've changed the diagram. Any questions? How many electrons does neon have? 10. It's written on the periodic table. If you look at this wall, neon's way over there, and there's this big number 10 on top of it. That's the number of electrons. It's like right there. So cool. Well, we've got one more spot here. Now it's neon. So now that's neon with 10 electrons. That's not a very good 10. 10 electrons. One S2, 2 S2, 2P6. Do you see how nice this orbital diagram looks? All the beds are full, right? Everything's just packed in there nice. There's no open spaces. It's just perfect. This happens with all of the noble gases. They fill up the rooms. The other elements, there's always some gaps here and there. The electron configuration of neon represents the complete filling of the n equals 2 principal shell. In the hotel, neon fills the first and second floor. And it turns out that's an extra special situation. It's extra stable. Okay? What's next? Well, we can abbreviate. You can imagine, I mean, we've just been doing small elements. You can imagine if you get down to like bismuth or something with 83 electrons, you're going to be drawing a lot of boxes, and your electron configuration is going to seem to go on forever. So we have a way of abbreviating this. And what we do is we take the electron configuration of the previous noble gas and just use the noble gas symbol in brackets. So let's look at sodium. We'll look at it the long way, and then I'll show it to you the short way. So sodium is element number 11. It has 11 electrons. So if we draw the orbital diagram, we know that 10 was neon. 10 filled it up, and so we're going to need an extra box this time. 1s, 2s, 2p, and this is 3s. And then as we go and put our 11 electrons in here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I didn't do those quite in order. 11. The electron configuration, 1s2, 2s2, 2p6, 3s1. Everybody okay with that? Kind of making sense now? It's weird. I'm not going to argue with you about that. It's weird. what does this one look like? The electron configuration for neon. That's the same as neon. We can think of sodium in terms of the electrons as being neon with one more electron. This part right here is the electron configuration for neon. So instead of writing that over and over and over again, we write neon in brackets. And so the abbreviation for sodium's electron configuration is it's neon's electron configuration with the addition of one electron in the 3s. So it's just shorthand. Does that make sense? Any questions? I see wheels turning. You can almost hear the squeaking, can't you? That was a chair. That's not somebody's brain. Let's write electron configurations for each of these elements. Let's use the noble gas shorthand. Question? I can. Oops. Okay, so let's write electron configurations. So looking at the periodic table, we find aluminum. Did you find aluminum? What is the noble gas that's just before aluminum? It's neon. So when writing the electron configuration for aluminum, we can start with neon in parentheses. And then what does it have extra after that? It's got 3s2 and 3p1. How did I get that? You know, this is so frustrating because in the next section, it's going to become so much easier. Let's skip to that. We don't have to do it this hard way anymore. We'll come back to these examples. Let's look at the periodic table first. I actually don't even want to do that yet. Where is it? Come on. Huh? Yeah, here. This is what I want to look at. So here's a colored-in periodic table. Over here, these two columns represent S block elements. How many electrons can fit into an S subshell? Two. Look, there's two columns in there. Now, why is helium over there? Because he's special. Yeah, good answer. He's one of those baby brothers. Like I've got Andrew up in my office. Who knows, right, what he's doing? He gets away with stuff. I'm just feeding him fruit snacks, right? Just be quiet, watch TV, and eat fruit snacks. Helium's like that. In some sense, he really belongs over here, but for the purposes of this table, it'd sure be nice if he'd be over here, but he isn't. So helium kind of belongs over here. But there's two columns. This is the p block. How many electrons fit in a p subshell? 6. How many columns are there? 1, 2, 3, 4, 5, 6. Huh, look at that. This is the D block. How many electrons fit in a D subshell? 10. If you count those, there's 10. What? This is the F block. The F room has 7 beds. How many electrons fit in there? 14. If you count those, there's 14 of them. What I think is just mind-boggling, Mendeleev set up this table in this arrangement before we had any clue what an electron was, much less how they were arranged. It's amazing. And here, you know, they discover quantum mechanics, and they don't like it, but it explains everything, and it matches up perfectly with the shape of the periodic table. I just think that's really cool. So we were just looking at aluminum. So here's aluminum. Aluminum, you can actually read its configuration off of the periodic table. The periods here correspond to the principal energy levels, or the floors in the hotel. The first floor, there are 2 beds in the S room. The second floor, 1 bed in the S room, 2 electrons. The second floor, there's this S room with 1 bed that holds 2 electrons, and there's a P room, 3 beds holding 6 electrons. On the third floor, there's the S room and the P room. Next up in price is the 4S room. Now these guys, that's a D room. That room is actually on the 3rd floor. You're like, okay, it's falling apart. Well, kind of, but not really. This is how I think about it. We've got a little pattern going on here, right? Doesn't it look like this part like sunk down and like it really should be up there? That's what it looks like to me. This is the 3rd level, but it's more expensive for some unknown reason. It's higher in energy, and we're not going to care about why. So this is 3D. It's this period number -1. It's this 3D. So 4S, 3D. This is 4P right here. And next we have 5S. Again, this is that sunken area. This is 4D filling up through here. Then 5P. 6S. Thankfully, we won't really have to get to this. Here we would get to the 5D, but then down here, this is actually the 4F. They sunk even further. They sunk so far that they fell out of the periodic table. No, they didn't. Really, you should take a pair of scissors and cut it right there and put these guys in the middle. Makes it way too long to fit on a piece of paper. That's my theory. Anyway, that's the 4Fs filling up, and then we'll go back and fill up the 5Ds, the 6Ps, the 7S, start on the 6Ds, go to the 5Fs, back to the 6Ds. It's all in there. That's the order of filling. You can get the same thing by drawing all those things and making the arrows or memorizing it. I prefer to look at the periodic table and see it. I'm going to make you guys, well, now I can't remember. I was going to give you the highest element that I was going to make you do, but I can't remember which one it is, so I can't tell you that. But let's look at aluminum. If we want to write the noble gas shorthand electron configuration, I'm going to go up a row and find the noble gas at the end. That's neon. So if we're doing aluminum, it's neon. And after neon, we go to the next row. This is 3, and the S block, we count 1, 2. So that's 3, S, 2. And then we come over here, and this is the 3P block, and there's 1 there. So that's 3P, 1. Now, we were going to do bromine, but I got tired of trying to do it the other way. So let's do bromine on this one. Where's bromine? It's right over here. So what's the noble gas just before bromine? Argon. So I'll write this one at the bottom. Here's bromine. So we're going to start with argon's argon's electron configuration. There's argon. And so we're going to add some more electrons on there. This is period 4. This represents 4s. 1 electron, 2 electrons going in there. So 4s2. And then this is sunk down a level. This is actually the 3rd level. 3D, we're going all the way across. You can count them if you want to. There's 10 of them. So that's 3D10. So now I'm here. This is regular again, 4th level, P. 1, 2, 3, 4, 5. 4P5. What do you think? Not that we can vote on whether we need to go with this or not, but any thoughts? Yes?
What's the deal with copper? I noticed it's not following the same.
We'll get to him. There are a couple of guys that are being squirrely. We'll get to them. Any other questions or comments? Yes?
So for aluminum, you have it as neon and then 3s to the second and 3p to the third.
Mm-hmm.
If you be able to translate that over to like lithium, but still in the same brackets, or does that not work?
Do you mean...
You put neon in brackets and then lithium.
Could I put neon in brackets and write the electron configuration for lithium? Mm-hmm. No, I couldn't, because lithium is smaller than neon. So I'd have to be subtracting. We could use helium, though. It's not going to save us much, but we could do it. So if we're going to do lithium, we could either write it all the way out, 1s2, 2s2, 2s1, or we could put helium in brackets and 2s1. Because we go from here, helium with 2 electrons to lithium with 3 electrons. It's this guy plus 1. Aluminum is neon plus 3. 1, 2, 3. Really, the periodic table should be more like a cylinder. So if you took a piece of paper with the periodic table and curved it around, it should go directly from 2 to 3, and it'd be a spiral. It's like looking at a map of the Earth, right? The map of the world. They always cut it. They have to cut it along one of the oceans, right? Because you can't make a 3-dimensional thing be on a 2-dimensional piece of paper. Any question?
Yeah, why don't you include the D-block elements?
Why don't I include the D-block elements for aluminum? That's a good question. So 3s and 3p are lower in energy than 3d. Do I have this in here? I'm looking for, what am I looking for? Sorry if I'm making you dizzy. Oops, there it is. So this is the energy level of each of these. And this is called splitting, where the 4s, the 4p, and the 4d, we think that they should all be on the same level. And for hydrogen, they are. But because of interactions between elements, they're actually not on the same level. The 4s is a lower energy than 4p. And this is split so much that the 4s is actually lower than the 3d. And that is somewhat disturbing, but we can't do anything about it. We're just observing what is. Yes?
Could you write an electron configuration for a compound?
Could I write an electron configuration for a compound? Not really, no. We do have ways of looking at what the electrons do in compounds. You can look at molecular orbital theory, and it's really cool, but we don't get into it in this class. We touch on it in 1A. Question?
So when I went for lithium, you use like helium and then 2s1.
Mm-hmm.
If you have like Li or lithium plus,
That's a good question. What if you had a lithium ion, right?
So I know like when you have a plus, you go left, you're losing an electron, so you go left.
Yeah, so if we were losing an electron, so here's, and we will talk about that, but we might as well start now. So here's the electron configuration for lithium, the element. Lithium ion has a +1 charge, so that means it lost an electron. So we're going to lose 1 electron. The electron configuration for lithium ion is 1s2. It's the same as helium. What we're going to see is a lot of these elements, when they form ions, they end up with the same electron configuration as a noble gas. It's really cool. Any other questions? So let's try to go back and do these. Where'd they go? These guys. We did aluminum. We did bromine. Let's do strontium. We don't have the cheater chart, but we do have the one on the wall. So if we're going to do strontium, what's the previous noble gas? Krypton. So we'll write the symbol for krypton with brackets around it. So we got krypton. And then we go to the next row, and we've got rubidium. What period number is that? What row number? That's row 5. So those first 2 squares there represent electrons in the 5s. The first 2 columns are S. The number comes from the row. And on that periodic table, it's actually written on the periodic table. This one's missing it, but you can count. So 5, S, and rubidium would be S1, strontium is S2, and we're done. It's kind of like a bizarre game, like learning a code or something. Too bad we don't have a decoder ring we could do these with. Okay, let's look at argon and write an orbital diagram. Okay, the orbital diagram doesn't have a shorthand to it. But let's look at the periodic table and use that to help us figure out what these different levels are. So if I look at hydrogen and helium, that's 2 electrons. That's going to be 1 orbital. That is the first level, and that's the 1s. Now I'm on to the second row of the periodic table, so this is going to be 2. There's going to be S first, 1 orbital that holds 2 electrons. Then there's a big gap in the middle, and we get over to the p block, right? The p block, there's 3 orbitals. They hold a total of 6 electrons. Because it's beds in the hotel. It's pairs of electrons. So we see on the periodic table there's 6 columns. That's 3 beds. Didn't mean to do that. So that's 2p. And after 2p, we're done with the second row. And so then we go to the third row. The first group there is the S block. 2 electrons that'll fit in 1 orbital. Then again, we have this gap in the middle, and then the next one will be 3p. And now we can see that we've gotten to argon. Argon is at the end of this 3p block on the periodic table. So you could just go and fill in all the electrons. Or now that we've drawn all these squares, you can say, okay, well, argon has 18 electrons, right? Now I'm going to go put in my arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Argon is a noble gas. See how nicely he fills up all of his boxes? You get a discount at the hotel when you do that. Bring in exactly the right number of people. Any questions about the orbital diagram for argon?
I had a question
Uh-huh.
about the electron configuration.
Okay.
When you use the noble gas, is that the acceptable way to do it? You always want to use the noble gas?
That's a good question. Can you always use the noble gas? Is it okay? It depends on what the question is asking you. It'll specify. So the most important time to know this is for an exam, right? I give you a multiple choice exam. I am not going to try to trick you to see if you know the difference between orbital diagram and electron configuration. So it would be multiple choice if I said, select the correct orbital diagram for argon. This would be the correct one, and then there'd be some others that maybe had some of the arrows in both sleeping head up in the bed, or there might be, some missing, or the box is labeled wrong. But I wouldn't show you an electron configuration and an orbital diagram and ask you to choose between them. On something that I grade by hand, like a worksheet or a lab, I'm not going to get real picky on that. To cover your bases, you could give both. The electron configuration, noble gas shorthand, if it doesn't specify, I think that it's fine to use the noble gas shorthand. If it says full electron configuration, or if it says do not use the noble gas shorthand, then don't. But otherwise, I think it's fine. After you do a few of the smaller elements, you've gotten plenty of practice. Not using the noble gas shorthand just means that you get to write 1s2, 2s2, 2p6, 3s2 over and over and over again. And I don't think we need to do that. Any other questions? I went off on a tangent there, but I did come back and answer the question.